Yeah, he's got it muted now. If I don't hear anything through this, then I'll let him know.
Do you hear it?
I think so.
Okay, so upstairs. Are they on your work class?
I'm not going to say it, but
Sorry, officially or unofficially? So officially with Ben Moore.
Okay, welcome everyone. We're very happy to have Dr. Joanna Drazkowska here from the Max Planck Institute for Solar System Research. Joanna did her undergraduate and master's degree in her native Poland, and then she got her PhD from the University of Heidelberg, did postdocs in Zurich and Munich, and then won an ERC starting grant, and is now a group leader at MPS. So Joanna is a theorist working in planet formation research. She's done some really innovative projects tied to all sorts of aspects of the problems in planet formation research. But I think particularly the most interesting thing that she's been working on lately has been tied to the planetesimals and how you actually form and evolve planetesimals and protoplanetary disks, which I think is the subject of your talk today on the emerging theory of planet formation. So please take it away.
Thank you very much for inviting me. So yeah, I will show you today a couple of results, but I think you should rather look at this talk as like a report on the state of the art of our planet formation theory field. And yeah, I will basically start with some motivation of why are we looking for this new planet formation theory. Could we maybe dim the lights a little bit more? I did it myself. Okay. So yeah, so you probably know that since roughly 30 years, we learned more and more about planets orbiting stars other than the sun. And I think the major takeaway that I take from the exoplanet science is that actually most of the stars that you see in the night sky, so the stars in our galaxy, have some planets to them. So planet formation process is really happening all the time, or has happened all the time whenever a star were forming. And another major takeaway is that these exoplanet systems are usually very different than what we know from our own solar system, and in general very diverse. So you have some systems that, for example, would have only terrestrial type planets and no giant planets at all. And you have also some systems that would only have giants and often extremely close to their central star, like much closer than any planet is in the solar system. But the most common type of the outcome for the planet formation for now seems to be something that we don't have in the solar system, and we call them super Earths and mini Neptunes. As the name suggests, these are the planets that fall exactly in between Earth and Neptune. So now, of course, the main question that my research is trying to address is what kind of planet formation process do we need to explain all this diversity, right? And explain the formation of the solar system and exoplanets within one unified framework. So why don't we already have it? I think is a valid question. So for this, I think I need to walk you through a little bit about through this kind of classical approach to planet formation, which was entirely based on the solar system and what it looks like. So the solar system, as you probably realize, has currently 8 planets. So these are Mercury, Venus, Earth, and Mars, closer into the star, and we call them terrestrial or rocky planets. And then we have 4 more massive planets, Jupiter, Saturn, Uranus, and Neptune, that are farther out. But what you can see in this plot is that the whole space, whole available space basically in the solar system is also filled with other stuff than the planets, and these are the minor bodies. So in this map, what you see is all the objects that we know in the solar system that are over 10 kilometers in diameter, and this is about 10,000 of objects. There are also a couple more that we know about, so especially in the asteroid belts, it's very bright, but this is basically because it's close by, and we kind of can relatively easily detect even smaller bodies there. So this observation that we have from the solar system, that it's so filled with these minor bodies, so asteroids and comets, led to assumption that these bodies would represent the initial condition for planet formation. So they would be like these basic building blocks of planets, which in planet formation theory, we call them planetesimals. So if you kind of try to cartoon, summarize the classical theory of planet formation that you can still find actually in many textbooks, the very first step would be that you, of course, have a disk surrounding a young sun, and the disk is basically mostly consisting of this hydrogen-helium gas, but then you have some percentage, like 1% of heavier elements that condense out as dust. And then for very quickly, this dust would sediment to the midplane of the disk, and in some process that is not really well defined in this classical planet formation theory, it would create these gravitationally bound objects, so the predecessors of today's asteroids and comets. And then these planetesimals, as we call them, would continue growing by mutual collisions in processes such as the runaway growth, which basically means that the planetesimals that were initially born a little bit larger would grow much faster and then will become oligarchs. And then these oligarchs will continue growing in the process that we call oligarchic growth, that is a little bit slower and basically means that they just sit there and clean their direct orbital neighborhood out of the leftover material. And then those oligarchs that grow large enough, quickly enough, which basically means when this gas disk, this hydrogen-helium disk is still around, then they can accrete the gaseous atmosphere like it happened for Jupiter and Saturn at least. And then those oligarchs that would not grow large enough, quickly enough, would stay around as the terrestrial type planets like the Earth. And like a big prediction from this classical theory of planet formation was that you would only form these gas-rich planets in the colder region of the solar system, so of the disk, which is beyond the so-called water snow line. This is where the ice is contributing to the solid cores. And also the gas is much colder, so you have more material, and the gas disk is much colder, so it's easier to gravitationally bind the massive gaseous atmosphere. But of course, as I already told you, the exoplanet kind of discoveries destroyed this view, because we have, for example, all these hot Jupiters that are very gas-rich and very close to their central stars. And another piece of information that tells us that this classical view on planet formation cannot really be correct is actually coming from a new research on our own solar system materials. So basically, recently the precision of the material studies, mostly from the meteorites, so kind of for our purposes, meteorites would be the pieces of these asteroids, or these primordial planetesimals that for some reason made their way to Earth, and then we can pick them up and we can study in the laboratory exactly what they are made of. So by studying very specific isotopic composition with the precision of one particle per million particles, people have been able to put dates on when these parent bodies of these meteorites have formed. And this is a plot from a review paper by Thorsten Kleine, where what we can see is the most interesting for us is the y-axis that tells you the time of the formation of parent body after, counted from formation of the calcium aluminum rich inclusions, which are the oldest solids that we see in the solar systems that kind of are in some of these meteorites. So the CAIs are 4.567 billion year old, so relatively easy to remember. And then this would be just a single million years, right, on top of these 4.5 billion years. And we can see that our planetesimals in the solar system basically kept forming over several million years, which is consistent with the lifetime of this hydrogen-helium disk. So we can basically conclude here that the planetesimals keep forming over the whole lifetime of the disk, which is in itself very different from this classical assumption that all these like gravitationally bound building blocks have formed very quickly and everywhere in the disk basically at the same time. So this again motivates us to revise this classical view of planet formation, and in particular what we have been doing is to go back to the very beginning, go back to the basics, and these beginnings would have to do with the process of star formation. So many of you probably recognize this object. This is the Orion Nebula, so one of the nearby star-forming regions that we can access observationally. And if we look very closely at its densest parts, we can start to see the individual stars that are in the process of their formation. And what we then see is that these stars are surrounded by the disks, just as we kind of already knew. And these disks may, again, seem very like full of dust that is absorbing all this radiation. But in fact, the dust is approximately only like 1% of this disk mass. So if you actually do the calculation and you calculate the number density of dust grains inside of this protoplanetary disk, you arrive at something like 100,000 particles per cubic meter, which is coincidentally the definition of ISO 5 class clean room that we use in our institute to put together the space hardware. So now the challenge that we have to go through is how, out of these very rare clean room-like conditions, you can put together these dust particles and you can create this very massive planetary cores. And like a good thing is that the reservoir of this dust that you have in these disks that would be like hundreds of AUs in size is like much larger than the dust that you have in like one clean room. So you just need to like help it to make it a way to stick together, right? And yeah, there are many processes that drive this evolution of dust. And the key piece of information is that these disks that are like the spots where the planets form are turbulent and are also subkeplerian. And subkeplerian means that the local orbital velocity of our gas parcel in this disk would be slightly lower than Keplerian, and this will have many consequences, such as the fact that these disks are turbulent also has a lot of consequences. So this kind of random motions would push our dust grains around and will trigger some collision speeds, of course. And then this subkeplerianity of the disk will also cause the different velocities for different grain sizes in terms of their systematic movements, such as this azimuthal drift. Also, the fact that the dust grains will kind of feel a constant headwind from this subkeplerian disk will make them lose their angular momentum and move inwards. And also, this drift speed will depend on size. And finally, we, of course, have the settling, something that we also see observationally. If you look at the disks in different wavelengths, you see that in millimeter wavelengths, the disks appear much flatter, typically, than in scattered light that would track the smaller grains that don't settle that well. And if you are interested also in very detailed description of all these dust evolution processes, then you can look at the very recent review paper that Till Birnstiel put on arXiv just at the end of last year. So yeah, all these processes together, they would drive our dust evolution. And in one of the aspects that I'm particularly interested in are the collisions of the dust aggregates. And we basically can take all these processes that I just named, and we can build models for our protoplanetary disk and calculate what kind of collision speeds do we expect from each of these processes. And this is what this plot is showing. So depending on the size of the colliding aggregates, you can kind of deduct what is the collision speeds in meters per second. And then you can ask our colleagues that work on in laboratories to perform experiments like basically corresponding to these sizes and to these speeds. So this is an experiment from a lab of Jürgen Blum in Braunschweig in Germany, where they collided 2 centimeter-sized dust aggregates with the collision speed of 7.4 meters per second, which is exactly what we expect. And you can see that this collision definitely does not lead to forming any larger dust aggregate than what we started with. And this is the problem that we call the fragmentation barrier in our planet formation studies. And this is unfortunately not the only problem. We also have the radial drift barrier. So I mentioned that because of this interaction with subkeplerian gas disk, our dust grains will kind of have to move inward. And this speed, again, depends on the grain size. We typically plot it in terms of the so-called Stokes number, but it's just proportional to the grain size, basically. So very small dust aggregates would be very well coupled. They would move with exactly the same velocity as the gas is. But then as you grow larger and larger, you have this peak where the speed becomes really high, so something like 30 meters per second, which would translate into losing 1 astronomical unit in just 100 years. So this is a much, much faster, of course, than the disk lifetime. And since the grain size for which this peak occurs corresponds to roughly meter size dust aggregates, this is called very often in literature the meter size barrier. So now a big part of my work was putting all this physics together and building computational models for predicting the dust evolution in protoplanetary disk. And this is one example of such a model that is made with the DustPy code, which is publicly available on GitHub. It was developed by Sebastian Stammler and Till Birnstiel in Munich, so where I worked beforehand. And this is a 1D model. So you basically collapse all the dimensions of your disk in just one, which is the distance to the central star. So the star is somewhere here, and then you go farther and farther out. And then on the y-axis, you have the particle size in centimeters. And the colors tell you how much dust of each size and at each distance from the star you have. So you can see that initially we fill the disk with submicron size dust. And this is what we kind of expect to get already from the interstellar medium as the disk is formed. And then when we play this animation, you can see is that what happens is that the disk, the dust that is closest in our disk grows the fastest. And then it hits this blue line, which corresponds to the fragmentation barrier that I told you about before. And then what happens is that the portion of the dust mass is returned again to smaller grains, right? So you have a very wide size distribution once you hit the fragmentation barrier. And then farther out in the disk and also at the later times, this green line becomes more important, which corresponds to the radial drift barrier. And this basically means that before your dust grain meets another dust grain to potentially collide with, it will already move inward, right? And then you end up with like a very narrow size distribution around this drift limit. And the white line is, for those of you who are very interested, this corresponds to this Stokes number of unity, so the maximum radial drift speed. But for us, this is a very important line to put on our plots because it's directly proportional to the gas surface density. So basically, just by looking at the white line, you can kind of see what disk is used in the model. And here you can see that this is like a disk that actually has some like a power law closer in, and then it has this like steep exponential cutoff farther out. And so basically this is pretty hopeless, right? Like you don't really grow to aggregates that are much larger than centimeter sizes. And also, you don't really form any planetesimals, and you don't really form any planets. Fortunately, people have found some sort of a solution for this fragmentation and radial drift barrier, which is called the streaming instability. And it's basically a process that lets you jump over all these problematic stages. So you basically grow your dust a little bit to the stage that we call pebbles. And these pebbles are basically defined by their ability to drift through the disk, so to decouple at least partially from the gas. And then you collect these pebbles together and you form planetesimals directly without like intermediate meter size and stages, right? So you go directly to gravitationally-bound objects. And the way this is done, this is shown on this animation. So you can imagine this is like extreme zoom-in model on a very tiny portion of the midplane of your disk. And the color-coded is pebble density. So you start this animation with only pebbles. And you also start initially with some noise, as you will be able to see it again when it comes back to the beginning. And an important piece of information is to make this like model successful is that you need to start with the pebble to gas ratio of roughly unity. So you require some enhancement already, or actually very significant enhancement over this typical value of 1% of dust in your disk. If you manage to do that, then the streaming instability, so this like interaction between this subcapillarian gas in the disk and a very like overdense dust medium will lead to this behavior that any overdensity will keep growing in density until you basically have clumps that are already gravitationally bound and will continue to collapse into your planetesimals. And one interesting property of these planetesimals that are formed this way is that they are very often binary objects. And this is actually exactly what you see in the trans-Neptunian objects population, which is thought to be very primordial and not really collisionally processed. So this is, if you read this paper, this is basically treated as evidence that the streaming instability was the process that at least led to the formation of planetesimals in our own solar system. And also these planetesimals born this way are actually quite large typically, so streaming instability would leave you with something like 100 kilometers in size, right? So anything that is like significantly smaller would come from collisions. So what you see in the asteroid belt is actually very collisionally processed. But now we are left with the question of how do you fulfill this criterion of having a lot of pebbles in one place to initiate your planetesimal formation process. And this is exactly a big part of my work that I think I get most recognition for, is that I was looking in these dust evolution models how you can connect it to this streaming instability that naturally are very computationally demanding models that only address a very tiny portion of the disk, but I want to understand in a global disk how can you make this work. And one of the locations that I proposed in my research, and I was also not alone, so was also another group led by Chris Ormel that proposed very similar things at the similar time, was that you can make it work preferentially at the water snow line. And so the water snow line will be this location that kind of divides the cold region in the disk where the water contributes to the solid abundance and where the water is in the gas phase. And there are at least two processes that help you then to make your streaming instability work at the water snow line. The first process is called the cold finger effect. And basically, it relies on the outward diffusion of water vapor and then its recondensation on dust aggregates that are already present outside. And then another process is that you also have increased stickiness of your dust aggregate, which basically means if you think about this fragmentation barrier, that this fragmentation barrier will come at larger sizes, right? So this apparently happens also to other materials that close to their melting temperature, they become very plastic, and because of that, they become more sticky. So yeah, this is why I think the snowline, which like would actually be present in any disk, right, would be a great place to trigger this planet formation process. And these are next results that I will show you about planetesimal formation at the snowline in a disk that is just forming. So this plot is currently empty because we start with the star formation and disk formation happens at the same time. And then on the top panel, again, 1D models. So we collapse all the kind of complications of the disk into just function of the radial distance. And then we will be tracing what our gas, dust, and water vapor, and then planetesimals will be doing. And then on the bottom panel, we will be kind of recording the history of planetesimal formation in this model. So then when we play it, you can very well see where the snow line is, because this is where the water vapor gets condensed, and it doesn't exist then in the outer part. And then also in the bottom panel, you see the water snow line as this bright blue line. And then the red are the planetesimals that are forming. And you can see that we start forming them before the disk formation stopped. So this is a very simple model in which the disk is forming from the inside outwards. So you start with a very small, very compact, dense disk that is then kind of getting more and more material over the timescale of roughly 500,000 years, and then also spreading outwards because of viscosity. And these all complicated processes, so the dust growth is also included there, and like some prescription for streaming instability that turns your pebbles into planetesimals. And then you see that the planetesimals already start early, and then take a small break, and then they kind of restart forming in this more classical disk stage, in which the disk is like already very large and then just accretes onto the star. So this is roughly consistent with what I told you about the evidence from meteorites formation timescales, that they kind of kept forming for several million years. And actually, there is even more in these results that is consistent with different classes of meteorites. And if you want to know the details, this was published in Science, led by Tim Lichtenberg in 2021. So yeah, now we have at least our planetesimals. Of course, the story is not over yet, because these are just 100-kilometer size objects, and we are talking about forming Jupiter and Earth and potentially other classes of planets. So I told you, one of the, in this classical planet formation theory, you would only grow by colliding planetesimals together. But this is actually, unfortunately, not very efficient, because planetesimals don't really care so much about the gas around them, and they very easily get gravitationally scattered by these close encounters. And in recent years, one of the major additions to planet formation theory is the concept of pebble accretion. So this basically relies on having some protoplanet that is already maybe a moon mass or maybe even a Mars mass, and then the gravity of this protoplanet combined with the drag from the hydrogen-helium gas disk around it will help your pebbles, so this kind of centimeter-sized objects, to settle on the protoplanet much more efficiently than it would happen for planetesimals. So this actually speeds up the process of planet formation. So you can basically now go from moon mass protoplanet to Jupiter core, which is roughly maybe 10 Earth masses in roughly 1 million years, which is 1 order of magnitude faster than in this classical theory of planet formation that had this huge problem to accomplish Jupiter core in time. So yeah, I told you about a lot of processes now, so I want to take a break from showing you the results and put all these things together, what I really like to do. So this will be a plot that I prepared for our review chapter on planet formation theory that was just published in this huge Protostars and Planet 7 book that I have seen some people here already have, and I don't have it yet, so I'm a bit sad. But yeah, so we have to cover all this scale from micron-sized dust grains to cores of massive planets. This is a lot of orders of magnitude, roughly 40 orders of magnitude in mass that you have to go through. And as I already started to explain you, a lot of different physics that is involved into this. So we start with the process of dust growth. I showed you some models for that. This leads us to the stage of pebbles, the pebbles that are defined by their ability to decouple from the gas and to drift inwards. And these are roughly millimeter to centimeter sized. And then you need pebbles to form your planetesimals in the process of streaming instability that will take you to these like kilometer, 100 kilometer sizes. And then the next what happens is the classical approach that you collide your planetesimals together, and also the pebble accretion that I just told you about. And there is actually a huge debate whether or not the region of pebble accretion and the region of planetesimal formation overlap or not. Like some people would tell you you need this stage of the classical planetesimal collisions to make them like a bit larger, like large enough to let them accrete pebbles efficiently, but this seems to be very model dependent. And then this brings you to the stage of planetary cores, so basically something in between Ceres and Earth size. And then you may or may not go through the period of giant impacts. We know that in the solar system, giant impacts definitely had a role, for example, for forming the moon. And then if you are large enough, quickly enough again, you may go through the process of accreting your massive gas atmosphere. And then, last but not least, something that I am not doing much work on, but is very important to mention, is the process of planet migration. So basically, the gravitational interaction between your massive planets and the disk will basically shuffle the planets around. And this is the process that is believed to form the hot Jupiters, for example, that you like still assemble them somewhere in this cold region of the disk, but then you move them close in because of this interaction with the gas disk. So what is worth stressing here is that we really don't have like a single model to cover all these stages of planet formation. This is something that we would really want to have, but this is a work in progress and very, very challenging, as you may imagine, because of all these scales, like both in the size but also in time aspect that you have to cover at once. But I think the one other reason why we don't yet have this is that it is very challenging to find a consistent narrative like all the way from dust to planets, because there is seems always something that we are missing, right? Like, okay, we couldn't form planetesimals because of the fragmentation and drift barriers. We found the streaming instability. Now we can form planetesimals, but not everywhere in the disk, maybe only at the snowline, at some locations. But then do you have enough of them? Do you have still enough pebbles around once you formed your planetesimals to grow your planets quickly? And this is not really aligning very well. So it's always seems like, there is this kind of missing piece that would make it work. And I will try for the rest of my talk to convince you that the missing piece that we need in planet formation are actually the substructures. So another big thing that emerged in the recent years, also shown partially responsible for that, for these observations that really let you de-resolve the protoplanetary disks. And what you see is that basically all the disks that you can resolve currently are not really smooth. So are not like what we kind of classically assumed about the disks, but they have these kind of rings and gaps that are seen actually not only in the millimeter wavelength. So what is shown here are the famous ALMA results from the Dishart collaboration, but also you see these substructures in the scattered light. And there are, again, many mechanisms that are proposed. A lot of research ongoing on whether these are some sort of instabilities that in these disks, but like one of the narratives is, of course, that there are already planets growing in these disks and are like changing the structure of the disk. And this, we know that it has to be true, at least in some cases in which we detected the planet in one or other method. So for us theorists, the substructures are great, and they are actually something that we call pressure bumps or pressure traps in our disk. So I told you before, you have seen this kind of plot, and I told you the white line tells you what the gas is doing. So you see here that the gas is doing something funny. It's basically going down and then going up again. And this would be our gap in the disk, and this would be our ring, right? So the pressure bumps basically reduce or even stop this headwind from the gas. So basically bring the gas closer or to the Keplerian rotation. And then for the radial drift of the dust, it means that it's either significantly reduced or is completely stopped. And then in this kind of a ring, you would collect, like would be a place to collect your dust aggregates. And also another thing is that you, of course, you enhance the dust density, which is great for this streaming instability process again. So this would be this location that you could have this pebble to gas ratio of unity, and you could trigger your planetesimal formation. So this is actually a plot from this kind of first paper that showed computationally that streaming instability can lead to planetesimal formation. This is from Anders Johansson in 2007. But also for Pebble, accretion is great because the headwind is slowed down, and this even enhances this Pebble accretion rate. And now we take a very quick detour back to meteorites, because I told you I moved to the Max Planck Institute for Solar System Research, and now I have to learn a lot and also try to connect my research to the meteorites. So this will be something that I think is an evidence that one type of meteorites that are called the carbonaceous chondrites actually formed in such a pressure bump. And carbonaceous chondrites are, as the name suggests, relatively carbon-rich. That's why they are black. And they also formed like relatively late in relatively cold region of the disk. So some people would say outside of the Jupiter orbit, for sure outside of the water snowline. And they, you can like broadly say they consist of three components. One are these calcium aluminum rich inclusions that are these white thingies, the oldest solids that you have in the solar system. The other would be the chondrules, which are like something like a molten droplet of rock that's solidified, and you can see that's what gives the name to the chondrites. And then the rest is filled with the matrix, which for our purposes is like this more fluffy dust aggregates that like fill the space in between. So also each of these components can be seen again in these like isotopic plots. So here we have the titanium and chromium plot. So for example, the CAIs would be somewhere very, very far outside on the top right of this plot. They have extreme anomaly in titanium. And then the blue dot here is our matrix dust isotopic composition. And then here would be our chondrules. And then you can interpret any meteoritical sample as like a mixture between these three components based on what is isotopic composition, right? So this is what the cosmochemistry groups are doing. And what they found here by putting all these samples from the carbonaceous chondrites is that the abundance of chondrules and CAI is actually correlated. So we are not filling all this space homogeneously, but we have this like a one stripe, right, that you can interpret as some sort of correlation, that the more chondrules, the more CAIs, the more chondrules you have. And what is even more interesting, there is an also correlation of this abundance with the time of the formation of the parent body. So the parent bodies that form earlier, so like farther out from today, they would have more of the CAIs and chondrules and less of the matrix dust. And the parent bodies that form the latest, so like after 4 million years after CAIs, they would be only matrix. So they don't have any CAIs and any chondrules. And I propose that the interpretation for this is actually a signature of streaming instability operating in a pressure bump. You need a pressure bump to correlate the abundance of CAIs and chondrules because they are actually different sizes, and the pressure bump would like all the sizes would put them all at the same location. But also the streaming instability tends to prefer grains that are like dynamically heavier, so of higher Stokes number, we would say, which basically mean either larger or denser than the rest, right? And this is what this kind of blue and green grains on this plot that is from the streaming instability study of By Stone in 2010 shows that the planetesimals would form like preferentially of the heaviest material that you have, which would, in our case, would be the CAIs and chondrules or aggregates that are containing significant amount of them. So the idea is that if you really had a pressure bump that collected all these components at the same place, streaming instability would kick in and would preferentially form planetesimals out of CAIs and chondrules, and the kind of matrix dust would come in play later, maybe after you already lost some gas from your disk, and then they would basically mean that your dust is becoming, again, heavier in this like Stokes number sense. So yeah, so this was the detour, and now we are back to like pure astrophysics results. So these will be results that from a project that was led by Tommy Lau, who is currently PhD student at LMU in Munich. And I heard that he will actually also be visiting you very soon. So if you have questions to his projects, then don't hesitate to come and talk to him when he is here. So what Tommy was doing was like truly this breakthrough kind of work where you put all these things together, like in terms of computational models. And for the first time, he has been able to stitch together the phase in which the dust is growing to pebbles, the phase that the pebbles are gone to planetesimals. So this is what I have been doing before. But now he also adds the evolution of planetesimals, both in terms of like these collisions between planetesimals, but also the pebble accretion, all this self-consistently because he does it in one framework. So now the bottom panel, again, the dust bytecode results that you already kind of know. You have 1D disk, you have the different particle sizes, and you put a pressure bump. And what this pressure bump is doing, so kind of inspired by the substructures, is collecting pebbles in one place and enhancing the density to the moment in which you can form planetesimals out of them, right? And then what the major takeaway from this paper that is actually already published in 2022 is that the fact that we do it in a pressure bump really speeds planet formation a lot. So you go from micron-sized dust to a several Earth mass planetary core in something like 0.1 million years, which is, again, order of magnitude faster than doing this in a smooth disk, right? So this was already very exciting, that we have been able to connect these like stages of dust and pebbles, planetesimals, and growing to planet. And then we kind of, for the first time, could self-consistently check like what budget of pebbles go directly to planetesimals, what part of pebbles would accrete in the pebble accretion process. And we found that this kind of pebble accretion pathway is actually very efficient. So like you form some planetesimals, then you lose your condition, but the planetesimals that form the earliest would kind of accrete pebbles so fast that this timescale will basically be the same as timescale for formation of the next planetesimals. So basically you limit how many planetary cores you can make if you consider all these processes together, because the planetesimals that form the earliest grew by pebble accretion and basically scatter around any newcomers, so kind of preventing them from growing into massive cores. But something was still missing here, and this is the very last part of my talk, the kind of feedback loop that you get once your massive planetary core starts to accrete gas, right? So you by accreting the gas and opening a gap in the gas disk, you again change the evolution of your pebbles, and you are impacting of like what is the follow-up evolution of your disk. So this is the last result that I have to show. What happens if you put all of this together? And this is still not published, but again, we have a little bit different visualization. We have now also our gas evolution. On the bottom panel, we have again our dust, but a little bit, kind of stretched into 2D. And this is to showcase, like, in more detail, the evolution of our planetesimals and planetary cores that now can also get atmosphere, and that would be indicated by this envelope. So again, we have our first substructure that will lead to relatively quickly to forming like some burst of planetesimals. And out of these planetesimals, we actually get 2 massive planetary cores. The first one will very quickly like start to open a gap. And the second one, because it's a little bit farther out, just because of gravitational interaction between the two, will take a little bit more time to join in and like accreting a massive atmosphere and opening our gap. And all this will lead to shifting this dust ring, so our pressure bump, farther out. But then with time, also the second, or the next planetesimal generation will occur from this bump, and this will again form 2 massive cores. But because it's actually already 2 million years after the start of all this process, you already lost significant part of gas. So these planets won't be able to become Jupiter. So they will stay rather at like Uranus, Neptune type of masses. And so by basically putting all these dust evolution, planetesimal formation, planetesimal evolution, gas accretion, the feedback to the gas disks together, it seems like we have something that like resembles a consistent scenario for forming a giant planet chain that could be Jupiter, Saturn, Uranus, and Neptune in our solar system, although, of course, in much more compact configuration that will actually be also consistent with the solar system studies, because you might have heard that we have something called the Nice instability scenario, in which you start with something like this, and then once you lose the gas, there is a massive instability that shifts these planets apart. So this is basically what I wanted to tell you today, and I will just leave you with some takeaway messages that we have a lot of progress now that is driven mostly by exoplanet discoveries and circumstellar disk observations, but also these laboratory studies of the solar system materials, something very new and like giving a great synergy to all this theoretical and observational work. And then I talked to you about these planetesimals, so the first gravitationally bound building blocks of planets. We know now they have to keep forming over the disk lifetime, but likely not everywhere. Maybe something like the snowline, maybe something like a pressure bump is what we need. The pressure bumps is something we definitely need if you want to form your planets fast. So if you want to have a chance of forming one or multiple gas-rich planets, you definitely need to slow down all this radial drift and like enhance your material density. And then the last thing is that if you connect all the stages together, you may get something like we would maybe call sequential planet formation process, in which you start like closer in the disk and you form the farther out planets later because of all this interaction of massive planets and the disk. So thanks a lot.
So questions from the audience?
So for the snowline helping with the planetesimal formation, if you have a source that's particularly bursty, say it's pushing the snowline out, is that going to do anything for changing how efficient planet formation is in that case?
Yeah, so this is a great question. I don't really have any model for that. Like I have an intuition that it may make it harder because it like break, let's say, the sequence that you have, like that I was showing in my 2018 paper, right, where like the snowline was just evolving because of the disk evolution, but there was no outburst here. Like if you imagine you push it out for some short time, I'm not sure like how the timescales will play into the snowline coming back into place. The farther you are in the disk, the harder it is to form planetesimals, because you like you take longer to enhance their density, right, and to actually form them.
So that was a great talk. So we know from exoplanet detections that we're getting giant planets out many tens of AU. And this model is sort of getting stuck at the 10 to 20
Yeah.
range. Do you think that's all explained by migration, or do you think there has to be another mode of planet formation out in the far reaches of the
I don't know the answer, but I can tell you that this mode that I'm showing here is not going to go out like up to 80 AU or 100 AU. I don't know what you need, like a particularly huge disk maybe some sort of gravitational instability, or maybe some sort of a perturbation that will give you this pressure bump really far out. But yeah, this is not easy to do, definitely.
So flipping the problem in the other direction for the very low mass stars, where we do see things huddled closely together, do you feel a pressure bump in those systems? Because you don't, the ice line is sort of all the way in.
Yeah, there are some actually studies of the planetesimal formation at the Iceland in context of TRAPPIST-1 formation, and it seems to work actually. Like you can form TRAPPIST-1 by like triggering planet formation at the Iceland and then migrating the planetary cores in and then getting them stuck in a resonance.
Yeah, great talk. How much mass is left in the disk at this stage, 2 million years?
That's a good question. Unfortunately, I don't have the plot, but I think it's not that much because the cores of these 4 massive planets, they ate up like 85% of what was initially available at all. So I think you probably have a couple, maybe 10 Earth masses, but I'm not super sure. This is something to ask Tommy because I'm sure he knows on top of his head.
Very nice talk. My question is how do you connect this model to the problem that you had at the beginning that was like the formation of mini-Neptunes?
This is the work in progress because we honestly, we know that this kind of process won't happen all the time, right? So the prerequisite of this happening is that you have this initial substructure that lives for at least maybe 0.1 million years that will let you kickstart this a first massive planets formation. My intuition would be that if you kind of maybe in some disk don't get this a pressure bump that will not only form very quickly the first planets but also hold them in place. Basically we kind of vanish our pressure trap, but then already the resonances between these massive planets will keep them will prevent their migration. But if you, let's say, start with this and you start forming something around the snow line or farther out, but you don't prevent it from migration, that's probably the answer for forming close-in super Earths and mini Neptune. But yeah, we don't have great models for that yet.
I'm a little surprised that this plot sort of looks so smooth. I'd expect there to be possibly more resonant related gaps and larger structure. Is that
you mean jumping around of the planets or
no, outer resonances of the existing planets ending up being cleared, or they're not just being one?
Yes, but our dust here is 1D. So our dust here doesn't really feel the direct gravitational influence of the planet, right?
Okay.
Yeah, for this, we have actually some models where we have the more 2D proper hydrodynamic model with the planet, and there you indeed see much more of these structures.
Okay.
Yeah.
Online question from Julie Elizabeth Mary M. Have you considered there may be a molecule involved in the accretion? In meteorites, there is low-density polymers that might be aggregator.
Something like a glue? That sounds no, we didn't actually, but yeah, interesting. Yeah, feel free also to contact me with if you have some suggestions, some ideas that emerge, you can write me an email or you can contact me on social media, whatever.
Joanna will also be here Thursday and Friday, so you can sign up on the link that I sent around. Okay, so let's thank Joanna again. Great talk.
Large that you kind of feel like you have to.
And until first certainly those graphs, I'm sorry, did you just something?
Yeah, it's like.
Hello. Very interesting. And is there any ideas about what could form the bumps?